Hello everyone. Today I'll be demonstrating my project on Altair Flightstream simulation software. I'll be demonstrating a simple simulation on UAV. I had first imported my CAD file, that is unarmed aerial vehicle, which was a drone which I designed it from a different software. I imported it to this Flightstream software via IGS model. So the model first will be retessellated and will be meshed by the software itself, and the model will be available on the working screen. Once the model is available on the screen, you can start working on the model. This is the model which we will be simulating today. It is a simple simulation with a simple design. So first we will take the model and cut it down to different parts such that our simulation will be much simpler, and it can be done on various parts with various loads or separated loads or separated conditions or boundary conditions or something like that. So we'll be taking the lasso tool and we'll select the wing actually. So first by the selection of rectangle lasso tool, we'll select the wing. Once the wing is selected, we will take an option called split into new body. So the body is split into a different body called body 2 from the assembly or from the basic model. Again we'll split the different wings, tail wings and the main wings separate. So completely we'll have 4 wings and 1 fuselage, such that we can apply like boundary conditions such as trailing edges only to the wings rather than to the fuselage, and also the base regions we will keep it only for the fuselage. So that is the main reason why we'll separate it. So once the body is split and separated, we'll start renaming it. So to rename the body parts of the model, we'll name it as wing R, just to make sure that we know what is what. So I have named it over here wing L, that is the left wing, and the left tail as tail L, and the right tail as tail R. Also here you can see that I have given separate colors for the separate body like model parts, such as the wings are of different colors, the tail are of different colors, and even the fuselage. So once everything is named, we can go forward with wireframe. So this wireframe tells you how the meshing is done by the software. As you can see, it is very beautifully done already by the software while importing it, but the amount of meshing what we need is for an accurate result is very less compared to what already is available. So what we will do is retessellate it. So first we'll select all the parts actually. Once we select the parts, as you can see, the value over here is 0.01. That is a very low value for meshing, so we'll keep the value as 0.04, which is an ideal value for our model. So as you can see, the mesh size has increased once we change the values. This is the ideal size which we'll be taking. There is no such as ideal size for your model. Based on the model and based on the results and accuracy you want, you can change the value of meshing. So we'll also rename the fuselage. We couldn't do it. Once it is done, again we'll go to the same option and we'll type in 0.04 and execute it. Yes, so we have a fully meshed retessellated model. So once that is done, we have to basically convert this CAD model into a mesh model. So in Flightstream, it is a very easy option to do that. Just select all the parts which you want to convert it into mesh and hold the shift key, and you can convert it to mesh. So once the mesh has been done, you can see in the mesh option that there is a plus sign which is showing. So yeah, the mesh is done. Once the meshing of the model is done, the option also will go to mesh. As you can see, CAD and mesh. So once the mesh is done, we have to check the topology. So once you check the topology, as you can see, there are no degenerated faces or edges with inverted faces, which is a good sign. All the paths, all the numbers in red should be 0. You shouldn't have any like numbers over there, or you have to change it. Also the free edges are 0, so that's a good sign. So next we will start assigning boundary conditions. So for the base regions here and trailing edges are the main boundary conditions which we have to apply. It can be easily applied by the software itself by auto detecting it. So base region, if you just press auto detect, there are 12 base region faces marked on the surface fuselage. Okay, that can be seen in the window below, and the demonstration of the base edges is over here. As you can see, these are the faces which are considered as base regions in fuselage. Okay, once the base regions are considered, we will start with the trailing edges. So the trailing edges is mainly done for noting down the air wind speed, like basically for the simulation on how the plane or the UAV runs and which way the fluid velocity should be taken place. So we have applied it to the wings and the tail wings also, trailing edges. Once the trailing edges are done, you have to point out wake terminal nodes. That is also can be auto detected. That is a node which connects the wing and the fuselage, so that vorticity should not be taken place. So we'll just choose whatever the body we need, and we'll just press auto detect by surface and it will get chosen. As you can see, we can see the wake termination nodes. After wake termination nodes are detected, you also can put in other boundary conditions such as free stream and inlets or turbulent edges. Here free stream is a constant, so that is not anything which we should mess around. So the fluid which we'll be simulating on is air actually. So, and again the properties of air also can be manipulated based on the parameters you want. So we have density, viscosity, sonic velocity, temperature, pressure, and ratio of specific heats. Then once you are done with it, you come to the bottom menu where the controls tell you all the features of your model, and then this is a runtime analysis where we decide the angle of attack, or basically the initialization of the simulation. So as we are doing it for subsonic simulation, we will keep the angle of attack as 5 and free stream velocity at 100 meter per second, reference velocity also at 100 meter per second. Convergence threshold, I have kept it at 1.00/05, and even the reference length is 1. The reference area I'll be changing it to 28.5 meter square, and also the parallel threshold to 28. We'll keep the minimum coefficient pressure at -20 itself. We won't do any changes in that. Once this is done, we can initialize the conditions. So to initialize, we'll go to the initialize solver, and over here we'll do it for subsonic. As there is no mirror symmetry, we keep it as none. We keep the wake as default, termination of X location, and then we start initializing it. It initializes within like seconds at as you can see 0.45 seconds. The initialization has been done for a steady state in subsonic, and also we can see all the trailing edges, groups created and everything as such. Then first we'll make sure it runs, or if we have any problems or any default or any, like if it doesn't run, then we'll make the changes again and we'll initialize the conditions. Again we'll go for the subsonic initialization. We'll just keep the model in the center. This is for coefficient of pressure at free stream. As we press the runtime, you can see the wake lines and also the data which will be converging. It converges at 159 somewhere, and the runtime also you can see it is at 0.00088. You can here check out other parameters like vorticity, boundary Mach number, velocity, Mach number, coefficient, pressure, anything, any parameters you want to see, you can look into over here, like boundary layer, separation marker, anything as such. Based on the result you want, you can look into it. Also you have plots over here where the graphs are plotted. So basically like residual velocity, residual pressure, or lift coefficient, drag coefficient, any value graphs you want will be provided over here. And also for getting the CSV analysis, we have to go to analysis and we get CL analysis, CDI analysis and CDO analysis. So here we have the practical values. We can compare this with the theoretical values and get to know the efficiency, or like we can map it with theoretical values and make the desired changes. This is basically for research purpose where we do it. So the next simulation what we'll be doing is for hypersonic, as this is for subsonic. As a UAV, it should be done for both the speeds, where it will be running at a lower speed and at higher speed. Most of the UAVs run at 3.3 Mach, which is the maximum. So keeping that in mind, we'll be doing the next analysis. So this is just the options which you can go into if you want to check it out. So the next number which will be setting is free stream Mach number. As I said, it will be set to 3.3, which is the maximum. The reference Mach number will be, we will keep it somewhere around 2.5 to 2.6. So yeah, and the other values remain the same. So again we have to initialize the solver, this time at hypersonic. So once we initialize, yes, again the simulation has been initialized and it is steady. So once it is steady, we can run the simulation. So yes, once the simulation is run, we get a coefficient of pressure. As you can see, the coefficient of pressure also varies, and velocity or Mach number, anything, again we can look into whatever static pressure ratio, whatever we want will be available. As you can see, there is a variation in the leading edge and trailing edge. The leading edge has a lesser static pressure, more static pressure, sorry, compared to the trailing edge due to the speed. And anyways, we can also compare the values. This is a velocity component. As you can see, the velocity at the leading edge and trailing edge varies due to the vorticity and other parameters. So based on these results, you can compare your vehicle or your model, how the performance, basically the performance of the vehicle in subsonic and hypersonic, and infer the CDI values and CDO values. Again, this also is available in based on graphs and analysis in analytical numbers. This can also be measured. Next, we'll also look into something like velocity. This velocity in y direction is completely zero, which means our model is completely perfect, as all the velocity component is acting only on x direction. So by this we can tell our model simulation is perfectly working fine, and the simulation which we have done is completely perfect. Again, when we go to the analytical results and refresh it, we have the CXC by CZ values based on the axes. Mainly we have CDI, CDO and CL values. So those numbers can be, like it can be evaluated, or you can use it to compare between subsonic and hypersonic or any other different results what you have got, may it be theoretically also. So this was my simulation. Thank you very much for watching my video.